This is part one of I don't know how many parts I'm going to do during the course of the build videos for this project. So this is basically the junkyard, or the where these broken equipment and machinery were kept, where I sourced all my hydraulic parts and other metals that I used to build this project. So this project is basically 100% built from recycled metals and machine parts. Like you are seeing, most of these metals are just being repurposed. Like all of these joints which I've collected here, different parts I've cut using a cutting torch, a gas cutting torch, and made holes using the same. So those are from old leaf springs, a truck leaf spring that were broken. I gathered those, put them together, and was able to use them for this section. So this part is one of two. I have two in that particular working robot, and I had to make two of these. So this is the second part, and this part is the one which houses one of the hydraulic cylinders. Like you can see, the one I've pressed in between, that is a hydraulic cylinder. An actuator, a correct term for it is called a hydraulic actuator. So this is the first part that I made. Then on the make videos, I'm showing you what I did to the second part. So this is the second part I'm doing, because they go as pairs. These are the ones which are correspondent to my legs on the machine. When I move the left and right leg, what I do is actuate the cylinders, the hydraulic cylinders, which are in these particular components. So I call these the muscle components of my legs, because whatever I do, if I lift the leg up, that up action on the machine comes direct from these actuating linkages, so to call them. Yes. So this was me greasing everything up, because I was greasing as I went. Technically, these were supposed to be built. If you were to build these on a mechanical standard, you would have to make sure you calculate for bolts in terms of removing them, maybe bolt and nuts, a way to secure them together. But like you can see, I was kind of working with time, so I didn't have the time to design the bolt fastening or any other kind of special mechanism of assembly. So I was mostly going for welding, where I can weld two parts together. I just had to weld them, and then I had to make sure to say if it required me taking it apart, of course I'll just have minor grindings to do, then I can take everything apart. But those parts which I knew to say these were standard, like for example the joints in this unit, I had to permanently weld them, but the pins are just duct weld in, because sometimes you may need to hammer the pin out. So that is basically what I did. I was greasing it up and finishing the assembly, putting in all the necessary pins so that the unit works freely. Yes. So this particular cylinder that I'm installing right now in this leg unit is for the forward and back movements. When it goes in and out, it will be making a pair or a set of legs. I can't say pair, because each one of these units is responsible for 3 legs. So the way I have 2 of them, one on the right, one on the left, it means it has got 6 legs. So those cylinders in the center were for moving back and forth. You can see where they went there. So right now I'm adding the middle cylinders, and these cylinders that are in the middle, they connect to each one of these leg units. And these cylinders will be responsible for lifting the legs up and down. So these are one of the main rod bearing cylinders, because this one cylinder had to be connected in a way that's calculated to handle the entire weight of the robot, because at times the robot may be required to lift up just using a set of 3 legs. So meaning that just this one cylinder, like the one I'm holding here, would be responsible for lifting the entire robot up on that set of 3 legs from the ground or uphill or up a stone, wherever. If I'm going up an incline, this would be the cylinder that would be in charge of lifting the robots up and down. So like you can see, I'm just doing some grinding there out of the support brackets that I made. One was too long, so it was touching the actuator, the hydraulic cylinder there. So I had to cut it down a little bit so that it fits, and the hydraulic cylinder may be able to fit. Yes. So what I meant by calculating, by making sure it had enough power to suspend or to lift up the entire robot just on 3 legs, that calculation comes in with the distances. If you remember the lesson of pivots and moments in physics, you would find that the longer the fulcrum is from the pivot, the greater the multiplication of the force applied. is far away from the pivot, then the road is closer, then whatever force is applied on the fulcrum would be multiplied. So that's why you see that this hydraulic cylinder is connecting a little bit higher compared to those pins, 2 pins on the end where that thing is swinging, where that unit is swinging from. So yeah, I had to do a little bit of alignment there. I had to put it in a little bit so that it can be going in freely. I had to make sure that everything was free enough to move by hands even before it was actuated by hydraulics. Because if it is stiff, I can't move it by hands, then basically that stiffness would also be, it would be an extra load on the system. So I had to make sure everything was free. Of course, greasing there, not forgetting to grease it. I had to grease everything as I went because I was working with time. Like I said, I only had a month and weeks to finish this project. So I had to make sure everything, once I do it for good. I didn't have to go back again. Like in a normal procedure, once you assemble everything, you try everything, you take apart everything again so that you can now have them painted, grinded, you protect them, you do some protective coating and everything, then you assemble it back together. And during that second assemble, it's when you do all the greasing and the other requirements required for it to be operating smoothly. But in my case, I only had about a month and some weeks to complete this project because I was fighting for a deadline. Yes, so the deadline that I was going for is for I wanted to present this project, to showcase it on the showgrounds for this year. So I had like just a month because I started this project in June. Yes, I started this project in June and this is July when it was completed. So it took me exactly a month and 3 weeks to complete this project because I was done with it by the 24th of July. I completed this project and it was ready for presentation. Yes, so I had to work with time. So working with time is usually difficult. So I had to move as fast as I could. I did some adjustment grinding there also, just to make sure everything aligns and everything is free, like I explained in the first part. So in this video, I'm just going to cover the chassis construction, how I constructed the chassis. If I say the chassis like in a vehicle, yeah, this is the main road bearing for the leg structure. So all the 6 legs are going to come out of this one, and the upper body of the robot is also going to be attached to this one. Yes. So I had to make sure everything is free, everything is aligned, proper alignment, all the leverage and moment advantages I was aiming for are correct. I had to feel them. Yes, I had to make sure where the pins were going were properly lubricated, they were clean of all grinding metals and stuff, because I wasn't going to go back to this again. It had to work from here going forward. Everything had to function as designed in my mind or as I planned. So normally someone would have all of these details sketched out on paper, calculated maybe in a simulation like AutoCAD or yeah, those softwares engineers use to calculate for things and do simulations. They would have done load bearing, metal strength. But here I'm just going with my knowledge and experience with regards to metals and joints, how to fabricate joints mostly. I know to say if I weld something like this, it will be strong enough to hold. I have to assume where the forces would be going. If at all there will be tension or compression forces, I had to foresee those. I had to make sure I foresee those and I see how the forces would be applied, because we're talking about hydraulics here, and as small as that cylinder looks, it applies a lot. Of pounds of force per square meter. So there I was just trying it with compressed air. I was blowing compressed air into the hydraulic cylinder just to make sure that they are free enough to move and nothing is holding. So like you can see, they are nicely going back and forth, and that is quite some force there. It's able to jack me up just from testing it. So everything passed. When I moved on to, this was one of the collecting rods. I have skipped a lot actually of fabrication and welding. Like you will see when we get back to the structure, there are a lot of other elements that were welded on, and those elements were like on that leg unit, it only had 2 legs attaching to it. That one unit had 2 legs attaching to it. Then the third one is on the opposite side of the robot. So like I said, it's supposed to have 3 legs touching the ground at all points. Since it has a complete set of 6, so 3 legs for each one of those leg units on the left and on the right. So I skipped the videos where I made the joining point for the third leg to the chassis, but I'll explain it when I show it. So this here, what I'm making is a link mechanism that will be linking the up and down movement of the third leg to the other 2 on the opposite side. So what I mean by on the opposite side is there are 2 legs on the right and 2 legs on the left. Then the third leg for each pair of for each set of 6 is on the opposite. For example, if 2 for the right leg, the 2 are on the right, then the third leg is on the left, on the other side of the robot, just to give it that tripod stability stance that I was going for, because they had to make a tripod stand, meaning that when it comes to standing on 3 legs, it has to be in a tripod setup. So there I'm just rolling I'm trying to come up with an eye where the pin will be going through. You will see when the link is completely welded. So this was the technique I used to roll one of these flat bars that I sourced from the scrapyard, and I used gases to warm it up. Then by light taps and shaking it, I'll be able to break it off from my former. That is a forming pin that I welded to the workbench, and I did a few tacks to make sure it doesn't unfold when I'll be shaking it back and forth, because I have to shake it in order to break those initial welds that I did when it was straight, in order for it to help me hold it back as I twist it around that pin. So yeah, like I said, all of these things were mostly going in pairs. So I did the first one. After I perfected the technique, this is when I recorded how it's done on the second pair. So the first link is already made and installed on the chassis. This is just the build for the second pair, so that you can get for the second link, so that you can get an understanding. It took quite some work to shake it off or to get it off, because all the welding had to be firm in order for it not to fail midway of me wrapping it around that pin. But yeah, it comes off smoothly. Like I said, this was when I perfected the technique. I had some challenges with the first one, but yeah, if you fail once, you try and try, then there I have a perfect eye, or rather hole. Yes. So in a normal setup, you would go for a thicker metal, then you drill a hole, you make sure it's rounded off, then you cut off that thing. So yeah, like I was saying, I was working with time. I had a time target, and this is a DIY project. I'm not working with new material and stuff. I had to do what I can with the materials that were available to me. So I had flat bars. That flat bar is 10 millimeters thick. So yeah, I had to work with it, because the thickness of 10 millimeter for my prototype, it would work for some time before it wore out. Of course, eventually it's going to wear out, because they're supposed to be proper, maybe bronze bushing or roller inside that hole, because a pin is going to be going through that hole, and that pin, that's the entire link that I'm building here is going to be responsible for lifting up and pushing down on that one leg on the other side of the robot in a set of 3. Yeah, so out of one hole, out of one forging that I do, I split it in half, then cut it apart in order for it to give me two pinholes for one link. Yes, so that was 1 and that was 2, and then I previously did the row, these other 2 which are here, so I made 4 of them. So this is the link that I was talking about, the link mechanism that will be linking the third leg to the leg unit that is on the other side. Yeah, so this is, I had to do all those angles and calculations in order for it to maneuver around the chassis and for it to be functional. Yes. So all those angles, like the way it is bending around, they are calculated because it has to sit in a certain way and be able to transfer the up and down movements of, like you can see. So this one is joining on the other side, like it's joining on the yellow leg unit, and then it's attaching to the other side of the robot. So it's coming like from the right, crossing all the way to the left, then attaching to the third leg that sits alone on the other side of the robot. So like you can see, it's coming from the bottom, and then on the other end it's attaching itself to the top part, because the movement has to be like the same. If these 2 legs on the yellow unit are going down, this other one has to go down as well. So usually in a setup like this, you'd find that you have to make the movement alternate. When that one is going down on the attachment to the chassis, that means when it's going down on that side, the cylinder will be pushing outwards, and when it's pushing outwards here, if you connected it to the bottom, like the way it is at the bottom to the leg unit on the yellow one, it would mean that this single leg on this side would be going up, it would be doing the opposite. So in order to cancel out that opposite movement, it had to be attached on top. So that other one which I'm touching is the first one I was saying, to say they go in pairs. So that is the link for the right hand of the leg, for the right side of the leg. Yes. That is how it was done. So yeah, these are the legs now that I was talking about. You see, I had built the legs, I attached them, I had the connecting bar already placed, then I was working on the pads now, because they couldn't just be bare metals. I had to make some kind of pads. So like you can see, this other one doesn't have a pad, this one here. So it's the pad that I'm going to show you how I made these pads, because they are flat and curved towards the end, because they want to move back and forth mostly. But as for the third leg, it has got a weird way of moving, in that in as much as it is moving back and forward, it also moves in and out. Because like you have noticed, those legs are moving on they have a swinging joint. So usually when something is swinging in GMD, you would carry, so they call it oscillating. So when something is oscillating, it never moves in a straight line. It kind of makes a curve from one point to another. So all those legs, actually, they move in curved lines. They don't move in straight lines. They move in curved lines. So as they are moving, so when you have two pairs, one on the left and one on the right, and those 2 pairs of joints are moving in curves, you would find that one has to, when they go out in the center of their movement, their curves are wider, but as they go outwards, it starts to narrow out. So I had to design it in a way that the third leg would be the one to compensate for the narrowing out. That single leg which stands alone on the opposite side of the robot would be the one to compensate for the narrowing out of those movements. Yes. So those 2 legs, when they stand firmly on the ground, they take most of the load. Then that other leg, the third one, the single one on the opposite side of the robot, is for balancing. So the one that does balancing would be the one to compensate for those narrowing and widening out during the swing of the during those swings of in movement. Yeah, so that pad that had to have some way in order to allow it to slide back and forth. That's why it's more of a rounded pad. It's different from most because it has compensate for all those movements. It should be able to slide inwards, outwards, back and forward. That's why I had to construct it differently. So in as much as it should be able to do all those, it should also be strong enough to bear the load at all points. Because in as much as it is moving back and forth, it is also going to be twisting around. So whenever it twists, it should, whatever part of it is touching the ground should be able to bear the weight of the entire machine. That's why you are seeing I'm using thick metals here. They are 5mm plates that I'm using to make this particular pad. Center there where the tube will be attaching to. Yes, all these videos may look like it's a single day, but they were shots taken out of different days. Yes, I had to take, since I didn't have a stand for my camera and I was using my phone, I just had to show some brief moments. So this is now the entire leg structure completed here, the chassis. I'm just doing some final welding. So these links you are seeing on this side, like that one with round things, those are the linkages that transfer now the forward and back movements from the right side of the machine all the way to the one leg that is on the opposite. Also on the left side of the machine, there is also a back and forward link that is transferring that movement around the entire chassis all the way to the leg that is on the opposite side. That's why in each build like this one, you would find that there are mainly two linkages attaching to that one particular leg on the opposite. One is that link I showed you, the thick one, the one I was building, like that one showing there, which moves up and down. Then there is this one, which is on the down part of the screen right now. This one, it's responsible for moving the robot. This one, it's responsible for moving that opposite end one leg back and forth. So that link pulls on it. It pulls it forward when the legs are going forward. It pulls it back when the legs are going back. Yeah, it was tricky coming up with these because, like you can see, they are complicated joints. Yes, complicated link mechanisms, because they had to do the opposite. In a normal setup, when you connect two things together in a sequence like this one, when you move something back, as it is moving back, it would pull the other one forward. When you push it forward, it would pull it. But this one had to do the opposite, like you see in videos. Yes, so this is about the chassis.